So good evening, everyone. This is the fifth session of our quantum computing and elliptic curve, Shor's algorithm series, and our fifth session is about how do we use the Shor's algorithm in order to crack the elliptic curve. So the elliptic curve. We tackled that in our last session, and let's have a review. So we have, as usual, we have Alice and Bob, which is the characters in our cryptography story. We just make this full screen. Okay, so Alice and Bob, they have they publish their public key based on the elliptic cryptography, and Bob, in order to send a message to Alice, he will use the public key of Alice to encrypt the message. So that's the typical public key cryptography algorithm. And now we have a eavesdropper by the name of Eve. She's able to see the exchanges between Alice and Bob. So that's typical, because that's the reason why we have public key cryptography. We are confident that the messages that we exchange with one another can be sent out in the public, because only the person who has the private key can decrypt the message. So given that it is based on elliptic curve cryptography, how would an eavesdropper decrypt the message? So if the eavesdropper, okay, so before we go there, so Eve knows the public key of both Alice and Bob. And Aaron, so because that one is public. So in this case, the public key of Alice is symbolized as P_A, which is equal to the private key of Alice, which is a number, symbolized as E_A, where A is for Alice, and P is the base point of the elliptic curve. Okay. So this is where the power of group theory manifests itself in terms of abstracting this, abstracting the concepts, the mathematics of elliptic curve cryptography. So in group theory, we have the definition of a group. Okay, so a group is just a set of objects which have an operation called multiplication, but the multiplication here is just a name that we give to the operation. So it doesn't need to be the usual multiplication that we know. Okay, so it's just the name of the operation. So so if for example in elliptic curve, our operation is actually addition. So when you add points, uh, the operation which is the plus sign is in the group theoretic um, definition, it is called the multiplication. Okay, um, so for example here, we know that uh, the private, sorry, the public key of Alice is EA times B. Okay, so if you go back here, it's EA times B. However, we know that EA times B in elliptic curve is actually equal to B multiplied to itself um, EA times. Okay, so for example, if EA is 3, so this becomes 3B, but 3B is equal to B plus B plus B. Okay, but in group theory, the plus sign is known as a multiplication. So that's so for example, if you multiply 3 to itself 3 times, then that's also equivalent to B raised to the 3. Okay, so that's why we can also write the public key as equal to B raised to the EA. Okay, where the group multiplication operation is defined as the addition of points. Okay, so B to the n is actually equal to B plus B plus B n times. And B to the 0 is the identity element, the point at infinity. Okay. So if B, if the public key PA is equal to B raised to the EA, then by definition of the logarithm, if you still recall the logarithm, we take the logarithm both sides. So the logarithm of P of A is just equal to EA times the logarithm of so the logarithm of PA with respect to the base B is equal to EA. Okay, so this one. Okay. So let me so what does that mean? Let me give you an example of what the logarithm means. So let's take a look at this one here. Okay, so remember that in for example the high school mathematics, if we have 10 raised to the 3 is equal to 1000, right? 1000. Okay. Okay. Let me write it properly. So 10 to the 3, that 1000 is equal to 10 raised to the 3, right? So according to the logarithm, the definition of logarithm, the logarithm of 1000 base 10 is equal to 3. Okay. So that's the definition of logarithm. So if we go back here, so if this is your 1000 is equal to 10 raised to the 3, then the logarithm of 1000 is equal to 3. Okay, so that's the definition of logarithm. But in this case, this is called the discrete logarithm. Okay. Yeah, so by doing a and why are we interested in getting EA? We are interested in getting EA because EA is the private key of Alice. So which means if you know EA, then you can read everything that every encrypted message that goes to Alice because you know the private key. Okay. Now, so how do we define? How does the eavesdropper get or compute the private key E of A? So if Eve has access to the quantum computer, she can use Shor's algorithm to find the value of EA. So the trick is to use Shor's algorithm. So the trick in using Shor's algorithm is to define a periodic function, because Shor's algorithm is very good at period finding. Okay, if you remember the last lecture in Shor's algorithm, we were trying to find the period. Okay, so Shor's algorithm is applicable to anything that is periodic, and it will allow you to find the period. So we have to create a periodic function in order to use Shor's algorithm. And to do this, we define a function called this one here, f of AB. So a function of A and B equal to B, where B, capital B is the base point of the elliptic curve, okay, raised to the A minus EAB. Okay, so as you see here, the A and B here are this one here, and EA. So A and B are parameters. B is fixed, as well as EA is fixed. Okay, so this is a function of A and B. Okay. Now, to show that it is a periodic function, what you need to do is for example, if you define A2 and B2 to be equal to this one here, then you will see that f of A1 B1 is equal to f of A2 B2. So if you have that kind of function, then that function is a periodic function. Okay, so where the period is k. So how do you show that? You show that using this one here, this computation. Okay, so f of A2 B2, you compute this first. Okay, so we know that f of A2 B2 is equal to this this term here. Okay, this is by definition of the function f. Okay, so definition of the function f. So let's try to do that, huh? So that you will also see how it's computed. So first, let's try to erase this. Okay. So what are we trying to show here? We're trying to show that the function is periodic. Okay. So the function is periodic. So the function is defined as f of AB is equal to the base point A raised to the B minus the private key multiplied by B. Okay. So if A2 B2 is equal to what was that again? If A2, B2 is equal to A1, B1 plus KEA1, okay, then F of A2, B2 is equal to F of A1, B1, okay? So how do you show that? So you show that by doing this. F of A2, B2 is equal to, according to this one here, okay, B raised to the A2 minus EA B2, okay? But we know that A2 is equal to A1 plus KEA, okay? So this one is A1 plus KEA. And we know that, so this minus EA, but we know that B2 is equal to B1 plus K, okay? B1 plus K. So B1 plus K. So this one is equal to B A1 plus KEA, and then you distribute this here, okay, to give you EAB1 minus KEA, okay? So which means that you can subtract this, okay? And this will give you B A1 minus EAB1, okay? So which means that if you compare this with this means that this is equal to F of A1 comma B1, okay? So in other words, it's a periodic function with period K. Okay, let's go back. And now that we have shown that it's a periodic function, then what we need to do the next is we are now going to use Shor's algorithm. Okay, Shor's algorithm. So we are going to prepare two registers in superposition and one output register. So here, this is our two registers, two input register and one output register. And if you remember superposition, so let me give you a a review. So if you have okay, so if you have an input register with for example, you have an input register with for example three qubits, okay, and you want to make a superposition out of this. So what you will do is you apply the Hadamard transform 3 times. Sorry, not 3 times, but you apply Hadamard transforms for the three of them separately. Okay, so this one is equal to h of tensor h of 0 tensor h of 0. Okay. Now this one is nothing but if you expand that, so we know that h of 0 is equal to 0 plus 1 over square root of 2. Okay. Now, so if you do this, if you substitute the value, you will end up with this expression. Summation of I is equal to 0, 2 to the n minus 1, and then you have here square root of 2 to the n. I. Okay, so this one is the superposition. So if we apply this in our in this expression, you will see that you have 2 input qubits, and you want to do superposition. So which means that you apply Hadamard to A and to B, you will get this expression. Okay, so 1 over P. The reason why it's 1 over P is because you have 1 over square root of P here and 1 over square root of P. If you multiply them, you will get 1 over P. Okay, so this is the usual Hadamard expansion. Okay, the superposition. Okay, so after that, you will apply the unitary operator, which is defined. We know that we have defined f, right? We have defined f to be this one here. Okay, so this one is our f. Okay, this one is our f. This one is our f. Okay, so we want to apply the f, the unitary operator u of f. So to do that, so you apply it to the input register and the output register, which is this one here. And by definition, this is equal to A, B, and then the output qubit will become the value of the output qubit will be the value of F, A, B. Okay, so that's the standard quantum computing operation, quantum computation. Okay, it's the standard. So if you do that, you actually apply u of f to the previous expression. Okay, so the previous expression is this one here. Okay, so you apply u of f here. Okay, which means that that expression will become something like this. Okay, so f is a periodic function. So now that your qubits, both input and output registers are in this state, the next thing that you'll do is to just measure it. Okay, so when you measure it, what will happen is that this the value of f AB will collapse into a definite. This will collapse into a definite value. Okay, and the input and the input register will then be a superposition of all values of AB, such that, because we know that this is periodic, diba? So since this is a periodic function, there are values A and B such that there are values A and B such that the value of FAB are the same. Okay. So how do I explain that? So for example, I'll just give you a example of what I mean by that. Okay, so I'll probably use this one here. So what does that mean? So let me use this. Okay. Okay. Sample. Suppose I have a set of numbers C. The sequence 1 to 100. Okay. And then I put an operation which is I define a periodic function. So in other words, I define a function so that whenever a periodic function, so that whenever I substitute one of these values, it will give you a number, but that number might be repeated. Okay, so for example, suppose I want to do the modulo of let's just say 5. Okay. Okay. Sorry, it's percent. Okay. So as you can see, in here you can see that the numbers are repeated. Okay, so 1, 2, 3, 4, 0, 1, 2, 3, 4, 0. Now suppose that this is the, just imagine that this is the output of your Shor's algorithm, okay, which is this one here. Okay, so when you measure the output register, it will give you a definite answer. Okay, so in this example, suppose the answer is 4. Okay, suppose the answer is 4. Now, what will happen to the input register? The input register will then be in a superposition of all those values whose output is equal to 4. So what are those values whose output is equal to 4? This is this one is 4, and then after that 8. Okay, so for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9, and then 10 is, and then after that 1, 2, 3, 4, so 14. Okay, so what will happen is that the input register will then be a superposition of 4, 9, 14, 19, 24. Okay, because those numbers, when you input it to the periodic function, it will give you the same answer. So for example, 24%, 5 will give you 4. 64% 5 will give you 4. 8% 5 will give you 4. Sorry, 8%, sorry, 9% 5 give you 4. Okay, so if you measured the output to be 4, then you expect that the input is a superposition of all these numbers: 24, 64, 8, 9, and many more. Okay, so that's what would happen to your input register. Okay, so in other words, the input register will then be in this form. Okay, because this one is a periodic function, it will give you all values of A0 and B0, all values of AB such that they have the same output. Okay, so what are those values of A and B? So you start with the first A0 and B0, and the next value which is the same, the next numbers A and B, which has the same value as f of 0 and B0, is A0 plus KEA and B0 plus K. Okay, so let me go back again. So remember this, okay? So we have A0 plus KAE, and then we have B0 plus K, okay? So let's go back here. Where's the okay, let's go back here. So what would happen is that this is the first value. Suppose that's the first value of A and B. Okay, so AB, that's the first value. So the next value, what's the next value? What's A1, B1, such that f of A1, B1 is equal to F0, B0. Okay, what's this? Okay, according to this, it should be A0 plus KEA, okay, A0 plus KEA, A0 plus KEA, and B0 plus K, okay, B0 plus K, okay. But if you take a look at this, A0 plus KEA, comma B0 plus K, that is this one here, okay? So that's so when you measure the output register, your input register will be in a superposition of all values having this form, okay? And M is the number of those values, okay? So which is not important to us, okay? We just know that there are M of them, okay? Where M is something we don't care. So now that you are in this, now that your input register is in this form, the next thing you'll do is to apply the Fourier transform to the input register. Now, by definition, the Fourier transform is defined as, if we go here, if we go back to we just take a look. This one is Shor's algorithm. Shor's algorithm series, session 3. So in session 3, which was the session session 3. We are already in session 5. We define the Fourier transform. Okay, so this is the definition of the Fourier transform. Okay, So let me write that here. Let me write that here. Okay, so there's a delay in my computer. So let me write the Fourier transform definition. Okay, so according to the definition, U of F, U Fourier transform of let us say a qubit z is equal to 1 over 2 to the n summation of y equal to 0, 2 to the n minus 1 e to the 2 pi I z times y over 2 to the n, and this one here. Okay. So in other words, the Fourier transform will transform the value of the qubit z into a superposition of basis vectors y. Okay. Now, if we apply that to this one, there's a lot of mathematics here, no? Pero it's actually quite easy to expand, no? So, for example, the first, if we apply it, this is the thing about quantum computing. You really have to take your pencil and paper and really expand this. Otherwise, you will just see things that you don't understand. Okay, so let's do this. Okay, so we begin with this superposition. Okay, 1 over the square root of n. Okay, summation of k equal to 0 to n. Okay, and the new Fourier transform of a0 plus KEA tensor product U Fourier transform of B0 plus K. Okay. Now, if we apply this, okay, so this one here, we apply this one, what does that give us? Okay. So it will give us the following. So the first one, it will give us this one here. 1 over, so what happens to 2 to the n? So this becomes a summation. So summation. This becomes a summation. So summation, let's do the summation first. Okay. Summation of just take it up first. Okay. X and y. Okay. So summation of x, x equals 0. Okay. Summation of x equals 0 to the p minus 2, and then you apply this one, okay? E to the 2 pi I, and what is z? Z is this one, okay? Z is a0 plus KEA multiplied by x over p minus 1, okay? Because there are p minus 1. So if since p is a prime number, then the set of numbers that are the set of numbers that don't have a common factor with p is the numbers 0 to p minus 1. Okay, and then so this is the first factor, no? This is the first factor, and then we have x, and then the second factor is similar, but this is from y to p minus 2. This is e to the 2 pi I. This one here, okay? B0 plus k times y over p minus 1, ky. Okay. Now, since this is a multiplication or tensor product, we can multiply this factor with this factor, okay, to get e to the 2 pi I. But multiplication is nothing but when you multiply when you multiply two numbers with the same two exponents with the same base, what you do is just add the exponents. Okay, so this is because they have the same base, which is e. What happens is that we just add exponents. Okay, so we just copy this. This is 2a 0 plus kea, okay, over p minus 1, and then you add the other one, okay, which is this one here, 2 pi I kb 0 plus k. So there's an x here, and then y, okay, and then we have xy. Okay. Now the next thing to do is to just simplify, no, rearrange terms. So what would happen is this becomes e to the 2 pi I. What's common? 2 pi I and p minus 1. P minus 1. Okay? And then this becomes a0 plus. So the x here will be distributed. Okay? So this becomes a0x plus keax, okay, plus distribute the y here, okay, so b0y plus ky, okay, and then xy. Okay, so what would happen to this one here? This one becomes what you can do is you can group a0 and you can group those that have k in common and those that don't have k. Okay, you can group this and group this. Okay, so this becomes a0x plus b0y plus k eax plus y. Okay, that's what happens. And then since if you take a look at this one here, we actually have a summation here, which is starting from k. Okay, so what we can do is factor out everything that don't have k and separate it from those that have k. Okay, so what happens is that this becomes e to the 2 pi I over p minus 1 um, a0x plus b0y, okay, multiplied by, this is the multiplication, e to the 2 pi I over p minus 1 time, plus, sorry, times k ea of x plus y, okay, and then we have xy. So we now put the summations, okay. So the summation here is um, we have summation of x, sorry, y is equal to 0 to p minus 2, and then summation of x equals 0 to p minus 2, and then summation of k equals 0 to m, okay. Now, since this one is an addition, we can actually we can reverse the order of the summation. Okay, so which means that we can sum first. You can do the summation first over k, and then we can do the summation over x and y. Okay, so what will happen is that this one will happen. Okay. Oh no. Okay. Hold on. My computer slept. You still there, guys?
Yes, sir. We are seeing your
Yes.
slide for quantum Fourier transform.
Okay. So what will happen is, so take a look at this part here. Okay, this part. So what will happen is that if we compare this with this one here, okay. So what will happen is I'll just move the summation inside. Okay. I just move the summation inside and left the two other summations. And this is what happens. Okay. So this one here. Okay. Now, so this is the state of your input register. Okay, so this is the state of your input register. So if you measure the input register, since the input register is in a superposition of x and y, if you measure it, it will give you a definite value of x and y. Okay, so it will give you a definite value of x and y. However, there are some values of x and y that are highly probable to occur. Okay, so if you measure it, you just don't get any other any random x and y that there are some values of x and y that are with that have a very high probability that have a very high probability of occurring. Okay, so how do you so the next thing to do is let's compute for the probability of these x and y's to occur. Okay, so the probability for these x and y's to occur is nothing but the um, the square of the probability amplitude. Okay, this one is the probability amplitude. This one here, starting from here up to here. Okay, so here up to here, probability amplitude. No? So this is the um, what you call this, the multiplier, or the number or the coefficient of your qubit, no? The coefficient of your of each possible values of x and y, so the coefficient. So according to quantum theory, um, if you want to compute for the probability of an x and y occurring, then you have to get the square of the square of the amplitude. Okay, but the square of the amplitude is nothing but this one here. So p minus 1 squared times m. Okay, so ito. You square this becomes squared. You square this becomes m. Okay, and then this one here. Okay, so this one. Now you might be wondering, oh, what happened to this one? Okay, what happened to this one? Well, the thing is, this one will, if you take the square of this expression here, it will just be equal to 1. Okay, so let me write that. Let me show you. Okay, so e to the 2 pi I, okay, a0x plus b0y over p minus 1. Okay, so let me show you the screen. The square of this one, okay, modulo squared, is nothing but this term multiplied by its complex conjugate. Okay, so this term, which is e to the 2 pi I a0x plus b0y over p minus 1 multiplied by its complex conjugate, which is e to the minus 2 pi I a0x plus b0y over p minus 1. Okay? But according to the law of exponents, this is just equal to e to the 2 pi I a0x plus b0y over p minus 1 minus 2 pi I a0x plus b0y over p minus 1. Okay? Since they are the same, they cancel out, which gives you e to the 0, which gives you 1. Okay? So that's the reason why this term here does not occur anymore in this probability, the square of the probability amplitudes, okay? Because it reduces to 1. Okay, now, if you expand this term here, if you expand this, if you let f be equal to EAX plus y over p minus 1, okay? Okay, if you let this one here to be equal to f, then you will find that the square is just equal to sine squared pi f m over sine squared pi f. Okay. Now there is a exercise that I prepared for you to be able to show that this is correct. No. This is the exercise. Where is that exercise? Sorry. Where's that exercise? Yeah, I think this is the one. Okay. Yeah. Okay. So according to this exercise, which you will show that this one here is equal to sine squared pi fm over sine squared pi f, where f is equal to where f is equal to this one here, okay, this one here. It's the same form, okay, so you can apply the same formula. Now let's suppose you have done that exercise and that you are convinced that this is equal to sine squared pi fm, then this function here actually attains its maximum when f is an integer, okay? So this function here attains its maximum when f is an integer. In other words, EAX plus y minus p divided by p minus 1 is equal to an integer. So what does that mean? It means that EAX plus y is divisible by p minus 1. Okay? So if it's divisible by p minus 1, then it has no remainder. Okay? Kaya that's why this one is another way of saying that it has no remainder. Because when you divide it by p minus 1, then the remainder is 0. Okay? Now, so if you have this, what does that mean? What does this mean? Okay? This means that you can now compute for EA. So EA is nothing but this expression. Okay? So let's derive that. So according to this, we have EA x plus y is equal to 0. Okay? Modulo p minus 1. Okay, so let me show you my screen. Let me show you this screen here. So in other words, EA of x is equal to minus y. Okay? EA is equal to minus y multiplied by x inverse. Okay? Where the inverse, where the x inverse, what does x inverse mean? Okay? So the x inverse, this means that okay, if you recall the definition of just say, so if you recall, there's a definition of the modulo, right? What's the definition of the modulo? According to the definition, so let us say modulo p minus 1, right? So according to the definition, the inverse of x is equal to that number. The inverse of x is equal to that number that when you multiply it with x, it will give you some number p, some number s multiplied by p minus 1 plus the remainder, which is equal to 1. Okay? So this is some number s, which we don't really care, as long as it's an integer, multiplied by p minus 1 plus 1. Okay? So in other words, x times x inverse is equal to 1 modulo p minus 1. Okay? So that's the definition of x inverse. Okay? We actually have the we actually have the code for that. So very naive code, but it will illustrate the point, no? So the point is that let's take a look at the code. Yeah, this is the code. Okay, this is mod div. So what will happen is that if you want to get the inverse of x, what you do is multiply x with some number I, where I is from 1 to 71, okay, or the modulo, okay. not including that number, okay? And then once you get, and then you multiply it with x and get the remainder. If the remainder is 1, then you have found your number, okay? And then return that number. That number is therefore the inverse of x. Okay. So going back, that's why we have this one here, EAs. So now, so in other words, you are now able to compute for the private key of Alice. Okay. So let's have an example. Now suppose after you measure the quantum, the input registers, you get x is equal to 51 and y is equal to 25. So when you get that value, you can then compute for the private key using that formula. Okay. So x equals 25, and then y equals 25, x equals 51 inverse modulo 70. Now it turns out that the inverse of 51 is equal to 11. And then you multiply 25 times 11 times -1 and get the modulo, you get the answer 5, which is the private key, okay? Which is the value of EA. So let's do that, no? So 25, so let's do first 51. What's the inverse of 51? Okay? So according to this thing here, if we use this, so ECC dot mod div of 51 70. Okay, so 70 is p minus 1, right? 70 is p minus 1. Okay, so this will give you 11, okay, which is this one here. Okay, and then you multiply 25 times 11. So multiply -25 times 11. Okay, and -25 times, minus 25 times 11. And you get the modulo 70, which will give you 5. Okay, so in other words, we have now computed the private key, which is 25. So once you have a private key, it's very easy now to decrypt. No? So suppose you're given this elliptic curve and the base point is 170 and Alice's public key is 4659, Bob's public key is 7054, and the encrypted message is 2539. Since you already computed for the private key of Alice, it's very easy to compute the message, no? So what you'll do is multiply the public key so what you do is multiply the so Eve, what Eve will do is multiply 75, which is this one here, 5, which is the private key of Alice, multiply it with the public key of Bob, which is 7054, and then get 4159. Okay, and then subtract it from the encrypted text, and it will give you the plain text. Okay, so let's do that. So 5 times 7054. Okay, so 5 times 7054. That's actually ECC dot mod mult. Okay, 7054 and then 5. Okay, it's 4159. Okay, this one here, and then we add it to 2539. we add the negative. Okay, so ECC that mod add what was that again? 2539. Okay, 2539 with 41 comma negative 59. Okay, which gives you the plain text. Okay, so that's it. We have shown how to compute for the private key given that we have a quantum computer. Okay, so and then once you get the private key, it's just a matter of, it's very easy now to get to decrypt the message that was intended for Alice. Okay, so that's it. Do you have any questions?